Okay, I think it should work. Um, are any of you on the admin team? Some of you don't have pictures, so I can't tell. No, okay, that's fine. I'll just get started. Okay, can everyone hear me and see the screen? Okay, someone just shout in yes. No?
Yes.
Yes? Okay, good. I won't be able to monitor the chat while I'm presenting. Um, so if I don't know if there is something critical happening, please just interrupt me. Also, feel free to interrupt me with questions during the talk. Um, okay. Yeah, welcome everyone. Thanks for coming to this pre-research advising session. My name is Fruzina, and I'm a new assistant professor in computer science. And today I'll talk to you about the research that is going to be done in my group, which features numerical methods, the design and implementation of numerical methods for challenging ordinary and partial differential equations. Okay, so I'm going to start with some kind of trick questions to sort of whet your appetite. So what do the following things have in common? The first thing is the color of this gorgeous mountain bluebird that is endemic to the Rockies. And the second thing is the sound that you hear when someone walks up the steps of the El Castillo temple at Chichen Itza. So think about that. And then the next two things are the origin of structure in the universe. What you're looking at are temperature fluctuations in the cosmic microwave background as measured by the WMAP experiment back in, I believe, 2012. And the motion of electrons in stellarators, which are a type of fusion reactors. The other alternative being tokamaks, but stellarators are kind of an up-and-coming fusion reactor design. All right. So, oh, and it spins. Okay, so the answers are, so when it comes to the mountain bluebird, even though it looks absolutely beautiful blue, if you were to kind of ground up its feathers, you wouldn't see any blue at all because the color is not due to pigment. So they would just look brown. It is instead caused by partly diffraction of light that hits the feathers because they have these microstructures in their feathers that are periodic. They scatter light in a very specific way. And that phenomenon is actually described by a partial differential equation, the Maxwell equations, which take the form of a Helmholtz equation. I'll talk about this later. And you have to solve that PD in a complex geometric setting. So because the scattering happens from a periodic structure. Okay, so how about the footsteps at Chichen Itza? So it has been observed that if someone walks up the stairs, then not only can their footsteps be heard a very long way away along the stairs, but they also sound kind of like raindrops falling into a bucket of water. So that's quite weird. And that acoustic phenomenon, that acoustic scattering, is also described by a PD. Again, it's the Helmholtz equation. And once again, it happens in a complex geometric setting, this almost infinite periodic surface. Right. And then the second two things are connected by a different equation. So the cosmic microwave background fluctuations are some of the earliest data we have of the universe. The cosmic microwave background was emitted a mere 300,000 years after the Big Bang, which means that at that point there were no stars. It was basically just primordial soup. And because of this, they actually tell us quite a lot about the origin of structure in the universe. And their early time evolution, so the early time evolution of temperature fluctuations or density fluctuations, is governed by an extremely oscillatory set of differential equations, ordinary differential equations this time. And a similar thing happens in stellarators. So the electrons They kind of circle around, they twirl around the magnetic field lines, which are visualized here. And so their motion has an oscillatory component and then also a slowly varying component. And in time, that is also described by an oscillatory ODE. So these are my main interests, kind of very challenging, either oscillatory or geometrically challenging equations. And I'm going to talk about each of them. But before I get into that, I wanted to talk a little bit about how I do research and what sort of numerical methods I'm interested in. So I build numerical methods with applications in mind, specifically physics and engineering applications. And my research blends numerical analysis, so kind of rigorous math, with scientific computing, including software engineering, and then also computational physics, so the application of these things to actual physical problems. And I'm interested in numerical methods that kind of satisfy the following criteria. First of all, they're adaptive, meaning that I want to require as little input from the user as possible, and I want the method to just figure out what to do. They have to be efficient, and they have to be high order accurate. So high order accuracy means that they stay efficient when high accuracy is demanded. On a graph, this is what a low order method and a high order method looks like if I plot the error of the method as a function of computational effort that the method requires. So you see that the high order method sort of its error falls off much more in a much steeper way than for a low order method. And what this means is that if you require certain tolerance, so if you want, say, 10 digits of accuracy, then you just need to put in less computational effort if you use a high order method. So, but why would you ever want 10 digits of an answer? I mean, usually in practice, 3 digits of accuracy is adequate. And the reason why in some problems you need to set a very low tolerance to the result is because the problem might be ill-conditioned. I will talk about this later, but this means that the problem is extremely sensitive to perturbations in the input. So the answer highly depends on exactly how you set up the problem and what parameters you give it. So in my work, I also focus on software. I believe that a method is only useful once it is implemented. And I tend to build open source software for this purpose. Okay, and then my background is actually in physics, and I'm particularly interested in astrophysical applications. So some of my applications are going to be into computational astrophysics. Okay, so in the first half of the talk, I'm going to talk you through some of my work on numerical methods for ODEs. And one of these, or the first one of these, is work on a frequency-independent solver for oscillatory ODEs, where by frequency, I mean the characteristic frequency of oscillations that occur in the solution of the ODE. But first, let's see why this problem is important to solve. So the sort of problems I'm interested in are given by this equation here. It's a second-order linear ordinary differential equation. It just has one dimension and one unknown. And it's posed as an initial value problem, meaning that we know what the unknowns are at the start of the solution interval. And you might see that there are two coefficients here, gamma and omega, which physically correspond to something that describes friction, and omega is something that describes frequency. And now the issue is, actually, I'm going to neglect gamma for the rest of the talk for simplicity. And what I'm going to assume is that these are real valued functions. The frequency is positive, and that it is large and smooth for at least some of the solution interval. And the issue is that if you just sort of try to naively solve this equation with something available from a large numerical library, then as the frequency goes up, so as omega grows, so does the runtime, and it will grow linearly with the runtime. So I say that the runtime is O, big O of omega. And this is because when a numerical method solves an oscillatory equation, the discretization length, so kind of how often you need to evaluate the solution, needs to follow the wavelength, which goes like 1 over omega. So the kind of discretization length that the method uses is going to be inversely proportional to the frequency. It's going to be shorter as the frequency grows. And this results in more computational effort. In fact, it makes it so that solution with these naive methods is prohibitively slow at large frequencies. All right. So, but then the other issue is that the behavior of the solution, U, may not be oscillatory for the entirety of the interval that we are interested in. And so a numerical method ideally needs to be able to handle this as well. So going into this, my goal was to design a numerical method whose runtime doesn't depend on the frequency at all. So it's just as fast for high frequency oscillations as it is for non-oscillatory behavior. And I was motivated by the fact that even though this seems like a simple equation, it's just one equation and it's ordinary and so on, it is ubiquitous in physics. It as I'll show it pops up in cosmology, it pops up in quantum mechanics and so on. And often one ends up needing to solve this equation, not just once, but 1 million to 1 billion times, especially if statistics are involved. So in a Bayesian inference or some optimization loop. Okay, and then, so before I started this work, the outline or the kind of the state of the field was pretty dire. There were no solvers available in numerical libraries that could even deal with large frequency oscillations. There were some very specialized solvers, but very few had implementations. And so often these equations were basically dealt with by hand. And then importantly, there was nothing available in large numerical libraries that most of us use. So my contributions to this are two methods. One of them is adequate for kind of typical accuracies that are required in physics applications, so 3 to 6 digits. And then the other one is so-called arbitrarily high order, meaning that if you want 12 digits, it will give you 12 digits and it will still be fast. And these I implemented as software, and they are published in the Journal of Open Source Software, or JOSS. So they share something something common. So the strategy that these methods take when solving a problem is that they're going to adapt their step size to what the solution does. So I'm going to call this step size H, and it's going to depend on the independent variable, which I'm going to say is time. And this step size is going to be adapted such that some measure of the error is going to be kept below a user specified tolerance, which I'll call epsilon. So they also will basically adjust their behavior based on what the solution is doing. So if it is oscillatory, they're going to do one thing, and if it's non-oscillatory, they're going to do something else. And this makes it so that these time steps, h of t, are going to be quite large. And this is what results in the short runtime and the frequency-independent runtime. So the strategy is to use two different methods, actually. One for when the solution is oscillatory and one for when it isn't. For when it isn't, I'm just going to use something very conventional. It's called the spectral collocation method, but you could also use something like a Runge-Kutta. These are basically all methods that are available in software libraries. So these are very established. However, for the large frequency, like the oscillatory behavior, I'm going to use something quite bespoke that I'm going to talk you through. And this is going to end up being something called an asymptotic expansion, meaning that it doesn't converge if you just kind of keep adding terms to this expansion. Right. And then at the heart of this algorithm will be detecting which method to use when. So the algorithm is going to detect whether the solution is oscillatory and then apply one method. And then when it's not oscillatory, it's going to apply another. And this is the result of that. So this figure shows you in black the analytic, so the closed form solution of a differential equation. And then the blue crosses and the red or orange dots are individual time steps of my algorithm, this oscillatory solver. And you see that while the solution is not very oscillatory right at the start, it takes these small steps denoted by the crosses, but once oscillations begin, it takes these huge time steps that actually span several oscillations. Okay, so the tricky part is this latter bit. So how do I get a time step to be so large so that it spans so many oscillations? And the trick here is instead of working in terms of an oscillatory solution, I'm going to work in terms of a slowly varying quantity, underlying quantity that I'm going to call the phase function. So because the solution oscillates, I know that it's a good idea to write it in this form. U of t is e to the integral of some function. So I'm going to work in terms of this function in the exponent because I know that if it's something like a phase, then it's going to be monotonically increasing and hopefully not oscillatory. So this function obeys a different equation, which is called the Riccati equation, and I write it here. It's first order, but it is nonlinear. And the issue is that if you were to just naively solve this, then it would be prone to like numerical oscillations. So it's not a good idea to just go and brute force solve it. So what I'm going to do instead is construct a solution to it. And I'm going to start from an initial estimate for the solution. It's going to be a function of time. And I'm going to keep refining it. So this is called the defect correction iteration approach. So if the solution is oscillatory, then I'm going to start from the initial guess of plus or minus I omega of t. If you substitute it back to that formula up in the first line, then you just get something that is an exponent, like an exponentiated phase. So this is a good zeroth order solution. It's actually the exact solution if the frequency were constant. It didn't vary with time. So I'm going to take this initial estimate and I'm going to measure how well it satisfies a differential equation. I'm going to do that by defining the residual, which is what you would get on the left-hand side of this equation instead of 0 if I were to substitute in the solution. So I define this residual, and then I will add a small perturbation or a correction term to my estimate, xj. It's the jth estimate in this iteration. And this little correction term is also going to be a function. And I'm going to set the left-hand side of this to 0. Why? Well, because I want the residual of this corrected version of x to reduce the residual as much as it can so that the next iteration of x satisfies the differential equation better. So this is what I get, and this is another differential equation, this time in terms of delta. I want to solve for delta. So I don't want to solve a differential equation again. So what I'm going to do is I'm going to start neglecting terms. The first term I'm going to neglect is this O of delta squared term. This is called linearization, and I can do it because I'm assuming that this is a small correction. So in magnitude, this term is a lot smaller than the others. And the next thing I'm going to neglect is the delta prime term. So this is a time derivative of delta. And the reason why I can neglect that is because I'm also going to assume that the correction term I'm adding is non-oscillatory. If you take an oscillatory function, say cosine of omega t, and you differentiate it with respect to t, then you get an omega term in front of it. If omega is large, then that means that upon each differentiation, the terms just grow. When something is non-oscillatory, that doesn't happen. So this delta prime term, hopefully I can convince you that it's actually order omega smaller than the rest. And if omega is large, meaning the solution is currently oscillatory, then it is much smaller than the rest of the terms. So you can compare it with the next term, 2xj delta. The xj is always going to be at least order omega larger. So I'm going to neglect that term as well. And what I'm left with is actually just an algebraic equation that I can solve. So I solve that for delta, and what I get is that delta is minus r of xj over 2xj. And what this gives me is it gives me how I can update from my initial guess for x. So the kind of the next iteration is just defined by this recursion relation. Okay, cool. So this was a pretty technical slide. So let me just go over it once again. So what I did is I changed variables from my original differential equation to something that's hopefully slowly varying, which I call the phase xt. And now I basically constructed a functional approximation for this function x. And it turns out that this approximation is especially good when the coefficients of my ODE are slowly varying or are smooth. And then this is basically what allows for large step sizes. Okay, so let's see it in action. What I did here is I plotted basically the error of my approximation for x as a function of the iteration number. So 0 here is my initial estimate, and I'm just adding correction terms, deltas, and I'm seeing how the error decreases as I approximate the solution of some differential equation that I wrote down here. And this differential equation has a frequency that's parameterized by omega max, and I'm going to increase omega max from around 10 to around 10,000. And what you see is that the error for each of the frequencies decreases, and it decreases in a geometric way, meaning by a constant multiplicative factor on each iteration. So notice that the y-axis has a logarithmic scale. And what this means is that for the largest frequencies, so in the purple crosses, I reach machine precision, so 10 to the minus 16 in about 5 iterations, meaning that these estimates for x and in turn for u are actually pretty good for when this solution is a symmetry. They're valid for a long period of time. Okay, but what I did so far is basically just did some analytic work, but this is not a numerical method. How does it, what I'm going to talk about next is how it builds up into a numerical method. So what I'm going to do is, while I'm solving the differential equation, I'm going to iterate over J to find a good approximation for this underlying quantity X. Then I'm going to have to transform back to the original variable of the differential equation called U. And this is done via this integral. Now, I could have started from two different initial estimates for x0, either plus or minus I times omega. This gives me two linearly independent solutions for U. Now, because the differential equation was linear, it means that I can combine these two linearly independent solutions to match the initial conditions. And this is what I'm going to do. So that's what I'm just writing down here. I have two unknowns A and B, which define the mixing of these solutions. And there is a matrix equation that I can solve to get A and B. Okay, so each numerical method needs three things. It needs a forecasting step. So it needs to forecast the solution from where you are currently to, the end of the solution interval or until the end of the next time step. But it also needs its own error estimate, and it needs an algorithm to adapt the step size. So the error estimate is going to be via the function that I defined earlier, the residual. So this is a measure of how well the ODE is satisfied. So the method that I introduced, it had some differentiation, it had some integration in it. I'm not going to do those analytically, I'm going to do those numerically, and I'm going to do that via so-called spectral differentiation or integration matrices. So don't worry too much about that. I'm just going to show you some results. So this is the ODE that I've shown you earlier. It takes this form. It's u double prime plus t times u equals 0. This is called the error equation. And I'm going to solve that over a very large interval. T goes from 1 to 10 to the 8. And you might see that the frequency, which goes as square root of time, it just increases over time. So, and the first plot, the top plot, I'm showing you the time steps that I've shown you before. And then below is how the step size increases as a function of time. And it actually increases. So the method just sort of gets faster. And then another important plot is actually how well it does. So how well does it preserve the error? And for this plot, so I'm plotting the relative error as a function of time as I'm solving this equation. And I set a tolerance of 10 to the minus 12 digits, that I'm plotting in the kind of gray dashed line. And you see that the method kind of keeps its error at around 10 to the minus 12, and then it starts going horribly wrong, seemingly. But it actually doesn't. So what I'm plotting in dashed blue is the maximum expected accuracy of any numerical method solving this equation. So this equation is one of the examples of, or is an example of ill-conditioned problems. I mentioned this at the start, but this means that if your initial condition was changed a tiny little bit, then the answer would change a lot as well. Now, in a computer, you don't represent numbers exactly. So you don't have real numbers. You have floating point numbers, which means that there is always a little bit of a perturbation added to the system when you solve it with a computer, because this computer is going to round the input numbers to floating point numbers. And the error it's going to generate, or the perturbation, is around 10 to the minus 16 if you're using double precision, meaning that any problem an ill-conditioned problem will amplify that 10 to the minus 16 error. And the amount by which it's going to amplify it is called the relative condition number. And this can be computed for certain equations. So this is how I got this blue plot, and you can see that the method is actually doing as well as it possibly can. Okay, so what I wanted to do is just compare my methods to the sort of industry standard, or other existing methods that have since popped up. So the ODE I'm going to do that on is, don't worry too much about it, is this thing on the left-hand side. Its solution looks like this. And its frequency, again, is a parameter. So I'm going to increase the frequency and see how well these methods do. So just to start off, I'm going to use a Runge-Kutta method, which is a very standard method. You can call that from pretty much any programming language. And as I promised at the start, its runtime, which is plotted on the y-axis, grows linearly with the frequency. The two lines that you see, the solid and the dashed, are the runtimes when I set two different tolerances, 12 digits and 6 digits. Now I'm going to start plotting all the other methods as well. So this is my previous work called Oscode. It does, and the important thing to see is if you look at the dashed line, 6 digits of accuracy, its runtime is basically flat as a function of frequency. So my claim that the runtime should be frequency independent is true. It doesn't work so well, however, for when you require the very high accuracy, such as 12 digits. There is another method out there that works very similarly, and it has the same problem. And then the two kind of best ones are this commerce phase function method, and then Riccati, which is my own work. And the winner is actually Riccati, because you see that the purple lines, the solid purple line, is about a 10 to 100 times slower, especially when you get to high accuracies. Okay, so time to talk about the implementation. So I have software implementation for both of these, and they are up to community standards in the sense that they are unit tested. They have online documentation, which I am showing some screen grabs of with tutorials. And they are available, they're implemented in C++ and in Python. And in Python, you can get them from PyPI or Conda. Right. And then what I recommend if you're also in the field of kind of software development, is get your code published in JOSS, the Journal of Open Source Software. It basically ensures that your software is up to community standards. Its review is open, and they're just extremely helpful in determining what needs to be done, what needs to be added to your code. And I'm in the progress of integrating one of my methods into SciPy, so it should hopefully be available soon. Okay, so having introduced this numerical method, I want to talk a little bit about where it can be applied. So one of the areas that I mentioned is cosmology. So this is the study of structure and evolution of the universe on the largest length and time scales. So one of the areas of application is for modeling the cosmic microwave background, the picture that I've shown you at the start of this talk. The issue is that modeling these fluctuations involves about 10 to the 3 oscillatory ODE solves for each parameter combination that you start your simulation from. So you want to simulate a bunch of universes with different conditions, and for each of them, you need 10 to the 3 solves. So what I'm showing on the plot there is a quantity associated with the universe, with these fluctuations, but you see that the plot moves. So from one frame to the other, I kind of changed the parameters of that universe a tiny bit. And this was only possible with a fast oscillatory solver. So if you want to do statistics of these universes, then you need about 10 to the 9, maybe 10 to the 6 different parameter combinations to start your simulation from. So that totals 10 to the 9 solves, which is a lot. Okay, so basically with a highly oscillatory solver like the ones I built, it became possible to look at models of the universe that previously people couldn't look at because they were just too computationally expensive. One example is something called a curved or a closed universe, which is now becoming a very popular model instead of the currently accepted flat universe model. So this is currently actually favored by data, and I'm very excited to work on it. And you see that actually predictions of certain cosmological parameters that I'm plotting here in this kind of corner plot shift if you use different models. So this red thing called Starobinsky is a closed universe model, and you see that it predicts a different number for H naught, which is the Hubble parameter, and it parameterizes the expansion rate of the universe. So these things have like physical consequences. Another application area that I have some projects available in is special function evaluation. Special functions are things like Legendre polynomials or Hankel functions, and they're used in all sorts of physical and engineering applications. Basically, they need to be evaluated quickly for a lot of these applications. And that evaluation can be done via recursion formulae, or they can be done via solving an oscillatory differential equation. And this latter approach has not been very attractive until the emergence of oscillatory solvers. So I'm just plotting some runtimes for solving for like different order Legendre polynomials, which is a type of special function. And you see that independently of the order, the evaluation takes on the order of a millisecond, which is very fast. And importantly, it's independent of this parameter mu, which is the order of the polynomial. Normally, the evaluation gets harder for high orders or for certain parameter combinations. So another nice thing that I'm interested in is that so if you evaluate these special functions by solving the underlying differential equation, then that approach parallelizes much better than evaluating them via recursion, which makes them a good candidate for implementing on GPUs. So this is something that I want to explore to optimize the evaluation of these special functions. Right. So that concludes that first half of the talk. And now I'm going to transition into partial differential equations in complex geometric settings. And the problem that I want to talk to you about is actually the one that I've shown in that second or so figure, which is acoustic scattering from a temple like Chichen Itza. So the reason why this setting is interesting is because we have some sort of source of sound, a point source, like a footstep or someone shouting. And it scatters off this surface, the stairs, which are long and periodic, so they're regular. I'm going to call this a periodic corrugated surface. So if I wanted to model that PD, there are some challenges associated with it. The first thing is that the domain that I'm solving the PD on is the exterior of the stairs. So sound only, it doesn't penetrate the stairs, it just kind of occurs in air, right? But that domain is infinite, it's unbounded. In PD solves, you normally have to discretize, so lay down some sort of grid on the domain that you're solving. But if the domain is infinite, then what do you do? So normally you get around this by kind of chopping off part of that domain, which is called truncation. However, for this sort of boundary that has periodicity in it, it's not a good idea to do that. And that is because it has been observed that sound and perturbations travel a long way across the surface. If you were to truncate the domain, then mathematically you would set the function that you're solving for to zero outside of the kind of truncated area. And that numerically results in something called an artificial reflection. So for that function to be zero outside, numerically you will introduce a reflected wave. But that is not real because the domain doesn't end there. So what that means is that you're going to have large errors. In fact, ordered one errors. So you're going to get 0 digits of accuracy. So truncation is not a good idea here. Another thing is that this is a very interestingly non-symmetric problem in the sense that the boundary that you're scattering sound from is periodic, but the source, if it's a point source, then that is not periodic. So you cannot exploit the symmetry of the system to make your computation easier. And then another thing that I'm going to talk about as well, it has, if you're modeling stairs, then the kind of tips of the stairs are going to introduce singularities in your numerical solution. Okay. However, it's an important problem. So these stairs or these periodic surfaces act as waveguides. They guide sound or radiation a long way across their surface. And this is used in industry quite a bit in things like photonic and phononic crystals, like seismic dampening, antennae, and so on. And often in material science, you need to tune the parameters of a material and simulate what the behavior of the material would be. So again, you need to solve this PD in a loop many, many times. So you need a fast solver. So what I'm going to talk about here is the results from this paper. And it basically details the accurate solution of this PD problem. And what it's going to use is the concept of something called trapped acoustic modes that I'm going to explain a little bit later. And in the process of solving this problem, we actually managed to explain that phenomenon that I talked earlier about why footsteps sound like raindrops at this temple in Mexico. Okay, so this is going to be a pretty technical slide, so just bear with me. We're going to solve a slightly different problem. I mentioned that what I want to solve is scattering of sound from a point source emitter, but actually I'm going to solve a different problem first. I'm going to assume that I have not one, but an infinite set of point sources arranged in a periodic way. I'm going to do this because that is a problem where I can exploit the symmetry to make my computation easier. And then I will basically be able to relate it to the solution of the original problem where I have just one emitter. So I'm going to solve for an infinite set of point sources. This is what the geometry looks like. So I have an emitter at x naught, but I also have emitters at basically each of these stairs. And the PD that I'm solving, and don't worry too much about this, is the Helmholtz equation. On the right here, I'm plotting just a single stair because by exploiting the symmetry of the system with an infinite set of emitters, I'm going to reduce the computation to just one of these stairs. This is called the unit cell, or like the repeating pattern of the boundary. It's a much smaller domain, and therefore my computation is going to be easier. So some notation, x is going to be my position vector, and the periodicity of the stairs is d. Now, the PD is linear, which means that I can break up the solution into two. UI is my incident radiation, and this is actually known. I can model what, like a human shouting would look like. And then the unknown is what's reflected off of the stairs, which is going to be US, or the scattered solution. Now, the solution has a characteristic length scale called a wave number. This is like frequency, but it's spatial, or it's like a wavelength, basically. Apart from the PD, I have a boundary condition, which expresses that this set of stairs is sound hard, so sound cannot penetrate it. And it's going to be a Neumann boundary condition. Again, you don't have to worry about this too much. And I'm going to introduce a concept called quasi-periodicity, which means almost periodicity. This means that because of the symmetry of the problem, the solution is going to have certain properties. So the property it's going to have is that if I move from my position X to the adjacent stair, so X plus D, then the solution is going to be almost the same. It's going to be different by a multiplicative factor that is a complex number. And it's always going to be the same complex number, no matter where I am. So this is called quasi-periodicity. And a consequence of this is that solutions with wavelengths that are 2 pi n over d apart, where n is an integer, are going to be physically equivalent. And then the last equation in the system, as I said, this is a complicated system, is something called a radiation condition. This means that I want the outgoing acoustic waves to not grow in amplitude. That is not realistic. So it just puts a constraint on the system. So the system I'm trying to solve is actually a differential equation and then 3 other conditions. Okay, so again, very technical slide. So just to summarize, I'm going to solve a different problem. I'm going to assume an infinite set of point sources that are quasi-periodic, which means that if I move by a period, the solution only changes by a set constant. And I'm going to have to solve the system of 4 equations. And then I'm going to go from this setup of an infinite number of point sources to a single point source via a mathematical trick that I'll introduce later. Okay, so I'm going to solve this PD via something called a boundary integral equation. So again, a slightly technical slide incoming, but I'm going to talk you through it. The idea behind an integral equation formulation is that the solution takes the form of something known. So the solution for the scattered wave takes the form of this ugly thing here. It's an integral, where that thing that I'm pointing to is a known function, and the unknown is this sigma of y. Okay. So basically writing the solution in this form will mean that it automatically satisfies the PD. However, the boundary conditions aren't satisfied necessarily. So if I substitute this into the PD and take the limit of approaching the surface and then write down what my boundary condition is, then I get a different equation, which is called a jump relation. Now, this equation is very ugly. It's this thing, where I is the identity operator and D is this integral operator. An integral operator is just an operator that has an integral in it. So this equation is now not a differential equation. It has integrals in it. It's an integral equation. And importantly, it lives only on the surface of where the scattering happens. So it lives only on the stairs instead of in 3 dimensions. Okay, so this is an integral equation. And the way I'm going to solve this integral equation is I'm going to discretize it, meaning I'm going to replace all of the integral signs with sums. And I'm going to do that in a way that approximates the integral well. And then I'm going to, instead of an integral equation, get a large matrix equation. And that matrix equation I can solve numerically. So the unknown here is going to be this sigma. And I'm going to, once I find sigma numerically, substitute it back to this first equation here and get what the solution is everywhere in space. So the big advantage of using this integral equation approach is that it completely avoids the unboundedness of the domain because it only exists on the boundary. So it's really good to use these on exterior problems. And it has a further advantage, namely that we went from like 3 dimensions to just a surface, 2 dimensions. And in that, we now need to discretize a shape, a surface that is 1 dimension lower than the original problem that we started from. And that reduces the complexity of the approach. So instead of saying using n squared evaluations, we only need n. Okay, so but the hard part is, how do I turn the integrals into sums? So that I do by picking quadrature nodes and quadrature weights. Quadrature just means numerical integration. Well, the issue is that that integral is actually singular, right at the corner of the surface, so like at the tip of the stairs. So what I need to be clever about this, and what I'm going to do is I'm going to divide the stairs up into these panels, and I'm going to define a numerical integral on all of those panels. But the panels get smaller as you get closer to the singularity, and they do that in a way that avoids the singularity. So this is called adaptive corner refinement. And yeah, don't worry too much about the other details. The point is that this is a nice way of ensuring that you don't run into that singularity. Okay. So here's the equation that we're solving again. It's an integral equation, and I wrote it in matrix form. But this time I set the right-hand side to 0 instead of what we had before. So I mentioned that the solution relies on something called the trapped acoustic modes. So these are solutions of my equation with the right-hand side 0. So you might recall from linear algebra that a matrix equation has a non-zero solution. A matrix equation like this has a non-zero solution if the determinant of the matrix is 0. So if it is singular. Otherwise, the only solution is no sound at all. So this is what the mathematical definition of a trapped acoustic mode is. But to give you some more intuition, this is what they actually look like. So in black, I have the stairs, and then blue and red just mean different, like areas of different air pressure. Red is excess pressure, and blue is areas of low pressure as the sound propagates. So these trapped acoustic modes they get their name because their amplitude is large, close to the surface, but then they sort of decay away. But there are several of these modes of different like length scales. And you see that first one here decays much more quickly than the next one. So I can find where these modes are by basically finding where the determinant of the matrix is 0. So that's a root finding problem, and I did that. And what that lets me do is compute something called the dispersion relation. So the dispersion relation relates the length scale of that like acoustic signal to the incoming frequency of the person that's shouting or the footstep. And you get something like this on the left side. And from the dispersion relation, you can also compute how quickly that acoustic mode propagates, so how quickly it moves down the stairs. And from this, you can create a very crude model of what a footstep sounds like. Because a footstep, I'm assuming, is going to excite all of the acoustic modes. So all of these different trapped modes. And they're going to propagate down the stairs exactly with this velocity that I computed. And from that, I can reconstruct how the sound distorts. Like each of these frequency components travel at different speeds, so they will arrive at different times. And as a function of time, this is when different frequencies of that signal will arrive. This is called a chirp signal. And this is what it sounds like. It sounds vaguely like a raindrop. So that's a reconstruction of that phenomenon. And now, finally, I'm gonna tell you how we go from this like infinite set of point sources setup to just a single point source. And the trick is it's completely mathematical. In words, what this equation means is that I can decompose a point source, which is the delta function, into a set of point sources where the quasi-periodicity is different. So think of this as a generalized version of the Fourier transform where you took some sort of non-periodic function and you decomposed it into a set of periodic functions. This is very similar to that. And the idea is that I have an integral on the right-hand side, and inside the integral, I have these quasi-periodic setups, and each of those I can solve very simply. So all I need to do is solve the PDE in a quasi-periodic setup and compute each of these solutions and then perform a numerical integral. That's it. Now, the issue is that that numerical integral is very difficult to do. So this is what the integrand looks like in the complex plane. And you see that there are some really nasty things here. I'm not going to go into too much detail, but those nasty things you saw are basically singularities. So there are two singularities called at minus kappa tr and kappa tr. And then there are these like discontinuities here, which are called branch cuts. And the idea is that when you integrate, you don't want to go near a singularity and you cannot cross a branch cut. So instead of integrating on the real line, I'm going to integrate in the complex plane. This is called contour deformation, and thus avoid those problems. If this went over your head, don't worry too much. The solution looks like this. So here I have close to zero, close to this central stair, a point source, and it's emitting sound waves. And you see that the solution looks like these like little lobes that travel outwards from this central source. So if you follow one, it just goes out. This is the real part of the solution, by the way, and this is the imaginary part, but the only thing we actually observe is the real part. Okay, so this is a snapshot of that movie, and my claim is that I'm not going to, prove to you is that this solution is accurate to 8 digits, which is completely unheard of with any other method. Okay, so we talked about these trap modes, and if you look closely, the solution from this kind of frame of that movie looks very similar to the plot of a trap mode. So these lobes that are kind of localized close to the surface, it looks like a trap mode. And it turns out that it is these trap modes that transport power away, like acoustic power away from the point source. And they're responsible for the steps being heard a long way away. So in practical applications, it is of interest to compute how much power is transported in them. So how quickly can they how quickly can the sound propagate away from this point source and how much of it you will hear. Okay, so numerically, it turns out that we can compute that via the residue of that singularity that I showed you in the complex plane. And it also turns out that infinitely far away from the point source, the only thing you hear will be the trap mode. We can do that numerically, and basically the results suggest that the most efficient at transporting power are those modes that are like most localized to the surface. So those that decay away very quickly. They actually end up being the highest frequency modes. So in industry, this is what you have to kind of optimize for. Cool. Okay. So, and I just want to finish up by saying what this could be useful for and what sort of projects I have in mind. So I'm interested in how the position of that point source and the geometry of the stairs or some other sort of scattering surface affect trap modes, their existence, and how much power is distributed among them. I'm particularly interested if whether we can induce asymmetry, so if sound can go one way but not the other. This could be really useful for the design of buildings, for example. And my idea is that in asymmetric geometries, this can probably happen. So these ideas here, I think could make good projects for either graduate students or like summer interns. I'm also interested in what this was a 2D setup actually, in the 3D generalization of this, where you have like an eggshell pattern for the scattering surface. And this is useful for seismic filtering. So the filtering of things like earthquakes, because that normally, and acoustic filtering, because that normally gets done by just layering a lot of insulating material, but that's expensive and the material is going to be heavy. So if by instead we can kind of modify the surface so that sound, it doesn't let through certain frequencies of sound, then that's a cheaper and a better alternative for filtering certain waves. Okay. And then finally, I'm interested in the inverse problem, meaning that so far we had a given scattering surface and we solved a PDE. We didn't know the solution. The inverse problem is we observed some solution, but we don't know what the scattering surface was because, for example, it was underwater or it was underground. And it's the inference of the shape of the surface that is the inverse problem. And then the last thing is that there is a different PDE that behaves in a very similar way called the Klein-Gordon equation. What I had is the Helmholtz equation, and that's relevant for topological insulators and superconductivity. So that's another thing I'm interested in. So thank you. I want to end this talk with another example of a beautiful bird that is not really blue, the blue jay. It has the same, it gets its color from the same phenomenon as the mountain bluebird. All right. So yeah, thank you for your attention. I'm happy to take questions. I'm going to stop screen sharing. I'm going to look at the chat now. Oh, okay, just yeses. Yeah, feel free to just shout in any question or write in the chat. Okay, and I guess if there are no questions, then I hope you enjoyed the talk and I'll end the recording.